Have you ever wondered how we can be 100% sure that something is true, not just today, but forever? In a world of changing opinions, mathematics offers the only absolute truth. But "it looks true" is never enough. Today, we are moving beyond intuition to unlock the structural secrets of the universe. Whether you are a university student or a logic enthusiast, by the end of this video, you will understand how to build an unbreakable formal argument. Let's dive into the core of mathematical proofs. Before we can construct a proof, we must master the grammar of mathematics. A mathematical statement is not just a claim, it is a structure built from logical connectives. Centrally, we have the implication, if P, then Q. This is the backbone of almost every mathematical derivation. It is important to remember that in formal logic, an implication is only considered false if P is true and Q is false. To express universal truths, we use quantifiers. We have the universal quantifier, which we read as for all x in S, and the existential quantifier, read as there exists at least one x in S. This level of precision is vital. In mathematics, we don't argue with opinions, we use these tools to ensure that our definitions are airtight. Remember, to disprove a universal claim, you don't need a long speech, you only need a single counterexample. This is the beauty of the negation rules, where not in parentheses for all x, p of x is logically equivalent to there exists an x such that not p of x. Every symbol we use here is a precise instrument on our journey toward mathematical certainty. The most fundamental method is the direct proof. To master this, we must agree on definitions. In number theory, an integer is defined as even if there exists an integer, k, such that the number equals 2 times k. It is odd if there exists an integer, k, such that the number equals 2 times k plus 1. A direct proof assumes the starting statement is true and applies these definitions and algebraic rules to reach the goal. This process relies on the closure property of integers, the fact that adding or multiplying integers always results in another integer. Sometimes a direct path is mathematically blocked. That is where the contrapositive comes in. In logic, the statement if P, then Q is logically identical to if not Q, then not P. If we want to prove if n squared is even, then n is even, it is often much easier to prove the contrapositive, if n is odd, then n squared is odd. Since these two statements are logically equivalent, proving the second one automatically and undeniably proves the first. It's about choosing the perspective that offers the most algebraic grip. Contradiction is the detective method, often called reductio ad absurdum. To prove that a statement is true, we temporarily assume the opposite, that it is false. We then follow the logical consequences until we hit a wall, a logical contradiction, like 1 equals 0. If our logic is flawless but leads to an impossible result, the only error must be our initial assumption. This is how we prove that the square root of 2 is irrational. Eliminate the impossible, and whatever remains must be the truth. We are diving deep into the mechanics of logic. If you are finding this breakdown helpful, please hit that like button right now and subscribe to the channel. It really helps us keep producing high-quality, rigorous educational content for you. Let's keep going. Mathematical induction is the domino effect of logic. It is a formal axiom used for statements involving natural numbers. To prove that a property holds for all n, we perform two steps. First, the base case, we prove it works for the smallest number, usually 1. Second, the inductive step, we prove that if the property holds for a number, k, it must also hold for the next number, k plus 1. We aren't just guessing, we are proving that the truth is inherited infinitely. Let's look at a famous example, the sum of the first n integers. The claim is that the sum of I from I equals 1 to n equals n times in parentheses n plus 1, all divided by 2. After verifying the base case for n equals 1, we assume the formula works for k. In the inductive step, we add k plus 1 to our sum. Through algebraic factoring, we show that the new sum follows the exact same formula for k plus 1. This proves the formula is true for every natural number in existence. Let's perform a formal derivation. Our theorem is, for every integer n, if n is odd, then n squared is also odd. We start with the definition, let n equal 2 times k plus 1, where k is an integer. Now, we look at n squared. That equals in parentheses 2 times k plus 1 to the power of 2. This is our starting point for the algebraic transformation. Expanding the expression, we get n squared equals 4 times k to the power of 2 plus 4 times k plus 1. We can now factor out a 2 from the first two terms. This gives us n squared equals 2 times in parentheses 2 times k to the power of 2 plus 2 times k, and then plus 1 outside the parentheses. Because integers are closed under addition and multiplication, the part in the parentheses is just another integer, let's call it m. Thus, n squared equals 2 times m plus 1. By definition, n squared is odd. QED. We have traveled from the basics of logical connectives to the rigor of induction and contradiction. Proofs are the bedrock of all mathematical knowledge. They teach us that every conclusion must have a solid, logical foundation. Mastering these techniques doesn't just make you better at math, it sharpens your mind to identify truth in all areas of life. Start with the definitions, follow the logic, and keep practicing your derivations. Thank you for joining this deep dive. If you enjoyed this level of substance, please like the video and subscribe to the channel for more advanced math and logic breakdowns. Share this video with anyone who wants to master the art of the proof. See you in the next session.